We imagine the Earth from where we actually live, a few meters above the ground, in a city, a town, or a landscape that feels familiar to us. At that scale, the world seems inexhaustible. We can spend years traveling through a single country without exhausting it, and the horizon, curved but imperceptible, gives the sensation that the planet extends indefinitely. However, in cosmic terms, that world we feel to be immense is a small, finite, and measurable object. The Earth is a sphere about 12,700 kilometers in diameter. If we could reduce it to the size of a classic 1-meter diameter ball in a square, all the continents, oceans, and mountains would be compressed into that ball. What for us are colossal mountain ranges, such as the Andes or the Himalayas, would barely stand out there as tiny imperfections on an almost smooth surface. The human scale is so small that compared to the planet, a person would be thinner than a speck of dust stuck to that ball. The very thin layer that makes life possible is the atmosphere. Although we visually imagine it as a deep sky, in reality, it is a very thin shell. Most of the air we breathe is concentrated in the first 10 to 15 kilometers above the surface, a height smaller than the straight-line distance between two neighboring cities. If we maintained the analogy of the 1-meter sphere, the entire atmosphere would be reduced to a film only a few millimeters thick. It is on that film where weather, clouds, storms, and everything we associate with the sky occur. Above that layer, the air becomes so tenuous that it no longer makes sense to speak of a blue sky, and space begins. There is no sharply marked physical boundary, but around 100 kilometers in altitude, conventional airplanes can no longer fly, and satellites begin to find suitable conditions to orbit. From that perspective, the Earth ceases to be a landscape and becomes a bluish disk suspended in darkness, a blue marble illuminated by the sun. In daily life, we tend to think of distances in kilometers, or at most in thousands of kilometers when we talk about traveling to other countries. Circumnavigating the planet along the equator involves traveling about 40,000 kilometers, a figure that on a human scale seems gigantic. But to begin to understand the true scale of the universe, we already need to introduce another type of distances, those that separate the Earth from other bodies in the solar system, starting with its closest companion, the Moon. The Moon is much smaller than the Earth, with a little more than a quarter of its diameter. However, when we see it full in the sky, intuition deceives us, and we tend to imagine it relatively close. On average, the distance between the two bodies is around 384,000 kilometers, about 30 times the Earth's diameter. If we placed our planet and the Moon as two miniature spheres, to maintain the correct scale, we would have to separate them much more than schoolbook drawings usually show. The space between them would be practically empty, with a large, dark gap where all the other planets of the solar system could fit in a row. That separation is large enough for light to take more than a second to travel from the Moon to the Earth. Every time we look at its illuminated surface, we are seeing how it looked just over a second ago. It is an insignificant delay to our eyes, but it introduces an idea that will be crucial when we leave the earthly neighborhood. In the universe, looking far away is always looking into the past. The farther an object is, the longer its light has taken to reach us. Until now, only a handful of humans have left the Earth enough to see the Earth-Moon system from the outside. The manned missions that reached lunar orbit covered that distance in several days, using enormous rockets and a considerable amount of energy just to escape Earth's gravity. Even so, their journey was barely a small step on a cosmic scale, a minuscule displacement within the sphere of influence of our own planet. If we transfer this entire scenario to a larger cosmic scale, the Earth-Moon system begins to seem like an insignificant corner. The distance that separates it is no more than a first step on a ladder of distances that grows vertiginously. Beyond the lunar orbit, the sun's influence dominates the movement of the Earth and the other planets, and the units we use for measurement stop being kilometers and become something new: the astronomical unit, the average distance between the Earth and the sun, the cosmic backyard, from the sun to the Oort cloud. As we move away from the Earth-Moon system, the scene changes completely. The dominating gravity is no longer that of our planet, but that of the sun, a plasma sphere 1.4 million kilometers in diameter that contains almost all the mass of the solar system. At this scale, the Earth ceases to be the center of anything and becomes a tiny point orbiting at an average distance of about 150 million kilometers, a unit we conveniently call the astronomical unit. The astronomical unit, or AU, is our new measuring stick. Light traveling from the Sun to the Earth takes about 8 minutes. What we see of the Sun is always an image delayed by those minutes. In comparison, light traveling from the Sun to Neptune takes more than 4 hours. Suddenly, minutes and hours become relevant for describing distances, and kilometers stop being an intuitive reference. When talking about the solar system, the numbers begin to lose scale in the human mind. If we look at the solar system from above, the first thing we notice is a disk of orbits. Close to the Sun, the inner planets, Mercury, Venus, Earth, and Mars, describe relatively compact trajectories. Beyond them, an asteroid belt marks a region populated by rocky fragments, remnants of planetary formation. Despite its cinematic fame, the belt is not a dense labyrinth of rocks. Its objects are separated by enormous distances. A spacecraft could cross it without ever hitting anything unless it deliberately tried. From Jupiter onward, the scale jumps again. This planet is so massive that it could contain more than 1,300 Earths inside it. Its gravitational influence alters the orbits of asteroids and comets, and it has partially acted as a shield for the inner planets, deflecting or capturing bodies that might otherwise have impacted closer to the Sun. Saturn, though slightly less massive, impresses with its rings, a structure of ice and rock extending hundreds of thousands of kilometers, but only tens of meters thick in many sections. Even farther, Uranus and Neptune mark the realm of the ice giants. Their orbits reach regions where sunlight is weak, available heat is minimal, and years last decades and centuries in Earth terms. What for us is the span of an entire lifetime can equate to only a fraction of a year on these worlds. Simply sending probes there requires carefully calculated trajectories and travel times that exceed a decade. Crossing Neptune's orbit, we enter the Kuiper Belt, a vast region populated by icy objects, including Pluto and other similarly sized bodies. This zone is a frozen archive of the early solar system. Many of its fragments have barely changed since their formation about 4.5 billion years ago. Yet even here, where we speak of a belt, reality remains the same, a mostly empty space, dotted with objects separated by distances that make the planets seem like distant neighbors. The probes humanity has sent beyond the orbits of the gas giants give a good sense of these scales. Missions like the Voyagers took years to reach Jupiter and Saturn, and decades to pass through the region where the solar wind still dominates interstellar space. Even traveling at tens of thousands of kilometers per hour, their progress is slow in cosmic terms. While generations pass on Earth, these spacecraft cover only a few tens or hundreds of astronomical units. Beyond the planets and the Kuiper Belt stretches the heliosphere, a bubble inflated by the solar wind, a continuous flow of charged particles that the Sun expels in all directions. The edge of this bubble, where the solar wind becomes too weak to dominate the interstellar medium, marks a physical boundary. It is the point where, for the first time, the direct influence of something other than the Sun begins to prevail. Some probes have already crossed this boundary, technically becoming objects in interstellar space, although they are still under the gravitational influence of the Sun. Even farther, on a scale we no longer depict on the same maps, models predict the existence of the Oort cloud, a diffuse sphere of icy bodies that could extend up to tens of thousands of astronomical units from the Sun. It is a reservoir of potential comets, barely bound by the Sun's gravity. Many of the long-period comets we see falling toward the inner solar system would have originated there, disturbed by the passage of nearby stars or by the gravitational tides of the galaxy. The ocean between stars, stellar neighborhood, and the Milky Way. From the hypothetical edge of the Oort cloud, the Sun is no longer the center of our story. It is just one more star in a sky full of points of light. The next leap in scale requires changing units again. We leave behind astronomical units and begin to speak in light years. The distance light travels in 1 year, moving at 300,000 kilometers per second. In human terms, it is a number so enormous that we no longer try to imagine it. We simply accept it as a practical measure to describe the space between stars. Our immediate neighborhood is formed by a few relatively nearby stars. The closest is Proxima Centauri, a red dwarf located just over 4 light-years away. That means the light we receive from it left its surface when on Earth we had not yet completed the current year 4 times in a row. If we hypothetically sent a spacecraft as fast as the fastest probes built so far, it would take tens of thousands of years to reach it. Interstellar space is not only vast, it is almost empty. Between one star and another, there can be light-years of distance with barely a few particles of gas per cubic centimeter. The Alpha Centauri system is not alone. Around it, within a radius of a few dozen light-years, we find a population of stars of all types: cold, long-lived red dwarfs, sun-like stars, and some more evolved giants. Many of them have planets, as evidenced by the thousands of exoplanets detected by space missions and ground-based telescopes. The emerging picture is clear. Planetary systems are not rare. They are the rule. Our own solar system is just one example in a vast population of possible worlds. As we move farther away, our point of view stops being centered on a particular star and begins to encompass the global structure of the galaxy we inhabit, the Milky Way. It is a disk of stars, gas, and dust about 100,000 light-years in diameter. The Sun is located far from the center, in one of the minor spiral arms, called the Orion Arm or Orion Spur, about 26,000 light-years from the galactic core. From there, it completes an orbit around the galaxy's center in approximately 200 to 250 million years. In the time that the Earth has existed, the solar system has made only a few turns around the galaxy. The Milky Way contains on the order of hundreds of billions of stars. Many are grouped in clusters. Others form part of the diffuse background of the galactic disk. There are gas clouds where new stars are born and remnants of explosions where others ended their lives violently. Among all this, space still dominates. Even within the disk, stars are so far apart that the probability of direct collision is almost zero, even when entire galaxies pass through one another. Toward the center of the Milky Way, stellar density increases and the disk thickens, forming a luminous bulge. At the heart of this region, observations indicate the presence of a supermassive black hole, known as Sagittarius A star. Its mass equals millions of suns, and its gravity governs the movement of the nearest stars. It is not a cosmic vacuum cleaner that devours everything indiscriminately, but it is the dynamic axis around which the orbits of the galactic core are organized. Beyond the main disk, a faint halo of ancient stars and globular clusters surrounds the galaxy. These clusters are compact spheres of hundreds of thousands or millions of stars, some of which are more than twice the age of the Sun. The halo also contains much of the dark matter that, although invisible, provides most of the galaxy's mass and keeps its components gravitationally bound. Without that dark matter, stars at the outer edges would escape into intergalactic space. The Milky Way is not isolated. It is part of the Local Group, a small family of galaxies held together by gravity. Besides our galaxy, the other major member is Andromeda, a slightly larger spiral located about 2.5 million light-years away. Nearby are the Triangulum Galaxy and several dozen dwarf galaxies completing the group. Viewed on a large scale, these galaxies do not form a chaotic swarm, but a structured system. They orbit a common center of mass, and in the case of the Milky Way and Andromeda, they are destined to approach and merge within a few billion years. When we observe the Local Group from even farther away, it begins to disappear into a sea of points. Each of those points is another galaxy, with its own population of stars, planets, and possibly life. The scale here is no longer only spatial, but also temporal. When we look at a galaxy hundreds of millions of light-years away, we see it as it was when Earth's history was at a completely different stage. Through its light, the universe shows us a record of its own past. Galaxy networks, from Laniakea to the observable horizon. When we stop looking at a single galaxy and expand the scale even further, the Milky Ways and Andromedas of the universe cease to be major individual players and become points within much larger structures. The first level of organization above a galaxy is the galaxy cluster, groups bound by gravity that share the same cosmic environment. Our own local group is part of one of these larger assemblies, anchored in a region of space where the combined gravitational attraction begins to dominate over the mere expansion of the universe. A prominent example is the Virgo cluster, located about 50 to 60 million light-years away. There, thousands of galaxies are concentrated, many larger than the Milky Way. From that cluster, looking back, our galaxy would be just one among many, a faint point on a map where the bright structures are entire concentrations of matter. In these clusters, galaxies orbit a common center of mass, interact, collide, and merge over billions of years, releasing enormous amounts of energy in the form of radiation and X-rays from the hot gas that surrounds them. Above the clusters appear superclusters, aggregations of clusters and groups of galaxies spanning hundreds of millions of light-years. It is at this scale that the idea of Laniakea, the supercluster to which we belong, comes into play. Laniakea is not a solid object, but a region of space defined by the flows of galaxies that, on a large scale, fall gravitationally toward the same area, a massive gravitational potential valley. Within it are the Virgo cluster, the local group, and many other galactic systems connected by this common dynamic. To imagine these structures, it helps to change again the way we think about the universe. It is no longer a space filled with galaxies drifting independently, but a three-dimensional network of filaments and nodes. This configuration is known as the cosmic web. In structure formation simulations, matter organizes like a kind of foam or spider web. Dense regions where many filaments converge, surrounded by large voids with very little matter. Galaxies align along these filaments, forming chains and walls that can extend hundreds of millions of light-years. The voids, in turn, are enormous low-density bubbles, regions with hardly any galaxies. Some of these cavities reach tens of millions of light-years in diameter. If a civilization were located at the center of a deep void, it would see a sky much poorer in galaxies than we do, simply because its immediate surroundings are less populated. The large-scale structure of the universe is not uniform in detail. There are denser areas and emptier ones, but on average, when considering volumes large enough, the distribution of matter becomes statistically homogeneous. In this context, the term observable universe takes on a precise meaning. From our position, we can receive light only from a finite region of the cosmos, limited by the age of the universe and the speed of light. The cosmological age is around 13.8 billion years, but the radius of the observable universe is greater than 13.8 billion light-years. It is estimated at roughly 46 billion light-years. The reason lies in the expansion of space. While light was traveling toward us, space itself stretched, increasing the current distance to the locations from which that light originated. Viewed this way, the observable universe is a sphere centered on us, but not because we occupy a privileged position. Rather, every observer, at any point in the cosmos, has their own observable sphere centered on themselves. What defines that sphere is the particle horizon, the maximum distance from which light has had time to reach us since the Big Bang. Beyond that horizon, there may be more galaxies, more structures, and more matter, but their light has not yet reached our position and in many cases never will. If we look toward the edges of that sphere, what we see are not well-defined galaxies, but extremely uniform radiation in all directions, the cosmic microwave background radiation. It is the thermal echo of the early universe, a fossil from when it was very young, dense, and hot, just a few 100,000 years after the Big Bang. At that time, space was filled with an opaque plasma. When it cooled enough, photons began to travel freely, leaving a trace that we now detect as a faint glow a few degrees above absolute zero. The background radiation marks the limit of what we can observe in terms of a direct image of the past. Before that moment, the universe was so opaque that light could not propagate without being constantly absorbed and re-emitted. To reconstruct what happened during those initial instants, we must rely on theoretical models and indirect observations, such as the abundance of light elements or the tiny perturbations imprinted in the background radiation itself, which over billions of years gave rise to the galaxies and superclusters we see today. Another key element in this picture is the expansion of the universe. For nearly a century, We have known that galaxies, on average, are moving away from each other, and that the speed at which they recede is proportional to their distance. The farther a galaxy is, the faster we see it receding. This relationship, known as Hubble's law, does not imply that galaxies move through fixed space, but that space itself is stretching. On local scales, such as within a gravitationally bound cluster, this expansion is cancelled out. On cosmological scales, it dominates. Current observations also indicate that the expansion is accelerating. Something, which we call dark energy, acts like a form of negative pressure driving the growth of space. In the long term, this acceleration has a direct consequence for the observable scale. Many galaxies we can see today will, in the future, lie beyond our cosmological event horizon. Their light, emitted at a given moment, will no longer be able to reach us. The observable universe, in terms of galaxies actually accessible to us, will gradually empty over time. At this point in the journey, we have reached the edge of what we can physically observe. A sphere with a radius of tens of billions of light years, filled with galaxies, clusters, superclusters, and filaments pierced by vast voids and enveloped by the faint echo of the Big Bang. But none of this implies that the universe ends there. Beyond that horizon, structures continue invisible to us, and cosmological models suggest that what we see is only a fraction of something much larger. To understand what might lie beyond our horizon and what this immensity means for a species confined to a small planet, we need to take one final step in our journey. That step will take us beyond the observable universe, toward hypotheses about what we do not see and the ultimate fate of the cosmos. Beyond the horizon, what we do not see and what it means to be here. Being in the observable universe is like standing in the middle of a fog-free plain with a curved horizon. You cannot see beyond a certain distance, but that does not mean the land ends right there. You know that beyond the horizon, the plane continues. In cosmology, something similar happens. Every observer, in any galaxy, has their own observable sphere centered on themselves, and these spheres overlap. What we see is a finite fraction of a much larger whole. The question of whether that whole is finite or infinite remains open, although observations point to a universe very close to flat geometry, consistent with an enormous, possibly unlimited, extent. To understand why our observable fragment is only a portion of something larger, cosmic inflation comes into play. According to this scenario, in a tiny fraction of a second after the Big Bang, the universe underwent an extremely rapid expansion, enlarging a microscopic region to astronomical scales. Our observable universe would be a small zone within that inflated bubble. Beyond what we can see, inflation would have left other regions with very similar properties, separated from us by distances so vast that, even with light traveling for billions of years, there will never be causal contact. Some models go further and introduce the possibility of a multiverse, not a single inflated bubble, but many, each with its own physical parameters. In this framework, what we call the universe would be only one of many disconnected regions, with physical constants possibly slightly different. For now, these ideas are speculative. They serve to explore possibilities and explain certain fine tunings of physics, but they lack direct observational evidence. The only thing we can state with certainty is that our horizon does not coincide with the edge of the universe, and that most of what exists lies beyond our view and always will. Within the portion we do observe, we have learned that ordinary matter, the kind that forms stars, planets, and living beings, is a minority. Cosmological data indicate that only about 5% of the universe's energy content corresponds to atoms. The rest is divided between dark matter and dark energy. Dark matter acts as invisible mass that holds galaxies and clusters together. It does not emit light, but its presence is inferred from its gravitational influence on galaxy rotation curves, structure formation, and the gravitational lensing that distorts light from distant objects. Dark energy, on the other hand, does not behave as localized mass, but as a property of space itself. It manifests in the acceleration of cosmic expansion, instead of slowing down due to gravity, as would be expected in a universe filled with matter. The expansion accelerates. In the simplest models, It is described by a cosmological constant, a uniform energy density that does not change over time. Other hypotheses propose dynamic dark energy, which could vary throughout the universe's history, altering its ultimate fate. Current observations indicate that dark energy dominates the total content of the cosmos and determines its long-term evolution. The ultimate fate of the universe depends on the details of that dark energy. If it remains approximately constant, the prevailing scenario is one of eternal, accelerated expansion. Over billions and later trillions of years, the galaxies we see today will drift away until they lie beyond our observable horizon. Locally, gravitationally bound clusters will continue to exist, but the background of distant galaxies will vanish from view, and the universe will become, from any vantage point, increasingly dark and empty in observable terms. This is known as heat death, a cosmos tending toward cold equilibrium, without energy gradients usable for complex processes. There are other theoretical scenarios. If dark energy were to increase over time in a certain way, a big rip could occur, in which accelerated expansion becomes so intense that it would first tear apart clusters, then galaxies, solar systems, and finally the very structure of matter itself. Conversely, if dark energy changed sign or decreased drastically, the expansion could slow down or even reverse, leading to a final collapse, a big crunch. Cyclical models have also been proposed, in which the universe alternates between phases of expansion and contraction. For now, observational evidence favors a cosmos that will continue expanding for inconceivably long periods, although uncertainties about the nature of dark energy leave other possibilities open. Meanwhile, on the scale of human life and civilizations, what does change is our ability to observe. Telescopes like Hubble and more recently the James Webb have allowed us to see galaxies formed when the universe was only a fraction of its current age. Other instruments, such as radio telescopes dedicated to background radiation, refine the map of the early universe with increasing precision. Each improvement in sensitivity and resolution pushes back the practical limit of what is observable, bringing us ever closer to the first moments in which the structures that populate the cosmos today originated.